4.1 is polynomial functions and modeling. So that 031 lecture that we just did is a really good introduction to it. So here's the actual definition of a polynomial. It says a polynomial function p is given by this equation where all the a's, guys, are just the coefficients, all right? And the reason why they have those little subscripts n minus 1, n minus 2, it just pairs them with the appropriate variable, okay? So this just means, hey, I'm the coefficient that goes with the nth term, so that's why I'm a sub n. But the key thing is all the coefficients a sub n through a are real numbers, so we don't have any i's or anything in there, and the exponents are whole numbers, and that's something that we talked about. You're not a polynomial if you're raised to the 1/2 power or a -2 or whatever it may be. So here are some of our more common ones. I want to point out some of these terms because you want to make sure you know what these are and how to find them, okay? So a quadratic function, what degree is it? Yep, so it's degree 2 or second degree. Is that all right? So what the zeros are, guys, the zeros, that's another fancy way to say x-intercepts or where you cross the x-axis. But how the book does it is the zeros are just the x values, like literally where you're crossing the x-axis, and then the x-intercepts are interpreted more as a point. And so they pair them with y equals 0, all right? How do we find zeros of a quadratic? You guys know how. You're going to either factor it, use the square root method, or the quadratic formula. That's what we just got done taking a test on. So you can find zeros any of those 3 ways. The y-intercept is where you let x equal 0 and solve for y. The minimum, we've already talked about. The minimum value is the y value of the vertex, right? So that's the y value of vertex. Where it occurs is the x value of the vertex. All right, maximum, if a parabola opens up, it's going to infinity. There's no technical max. But since it's opening up, it does have that minimum. If it was flipped over, guys, it would have a maximum and no minimum. So it's just kind of vice versa. And then, of course, domain, we're spreading out. We're going from left to right, so we're covering every number. So that's why the domain is negative infinity to positive infinity. We can plug in any x. It doesn't matter. But then, of course, the range starts from the lowest value of -4 and goes up to infinity. All right, so let's kind of like, we don't really need to do it here, but the cubic function, what do we notice about its degree? Degree 3. Hence the word cubic, right? Not anything really different to tell you. Notice that the zeros, again, are where your function equals 0, and then they pair them with the function being 0 to get the actual x-intercepts, all these same things. These we would have to do with a calculator to find those max and mins, and I'll remind us how to do that on our calculator using our trace feature. We can't find maximum mins in here. You'll be able to do that when you get to anybody going to calculus?
I think you have to take another math class.
But not calc probably. Is anybody going to calculus? You might have to. Okay. So in calculus, you're actually going to have the skill set to find these max and mins algebraically. But we don't have to do that in here.
Business calc?
Business calc is the same thing. So you might have to take that. Yep. So you'll be doing it there as well. All right. So then not a whole lot going on here other than notice the range since the ends are going. Remember the odd and even function we just talked about? Since it's odd, the ends are going in opposite directions, so it means we're going to negative infinity and positive infinity, so we cover everything. The only other thing I would like note on here is one that we don't have. It's called the quartic. And do you want to guess what its degree is? Yep, degree 4. Quintic would probably be, I don't know if that's really 1, but that'd probably be 5, right? So kind of just keep that in mind. So those are probably the 3 most common, quadratic and cubic being the most common. Is that all right? So on the next page, again, not a whole lot for us to write, but I do want to kind of like write notes here and there. On the top of the second page, you'll notice that we have some examples of polynomial functions and some that aren't. And it's kind of hard, so you might have to draw them a little bit better, especially these. This is the absolute value one, so it's just kind of like that V. This is a kind of a curve, like curved V. This was, remember our square root function, guys? We're just kind of that half arm of a parabola. And then this is called a hyperbola. like that. So the key thing to first of all notice is that their graphs are kind of funky, right? I mean, we have sharp edges. So notice here we have like a sharp edge here and here. We have weird gaps, right? A gap here, and we don't cover the whole domain and stuff. But the key thing to know why it's not non-polynomial is not just because the graphs are weird, but the degrees are weird. Like, how would you label the degree of an absolute value function? I don't know. What is this? This is a square root. What is its degree? And so notice they don't have that easy, oh, it's to the third degree or the fourth degree. And that's what makes it a polynomial. So if you go over here, this is the second degree. It's just a parabola we're used to seeing. This is technically to the 0 degree. It's just a constant. That's fine. That's a polynomial. This is to the third degree. This is that quartic to the fourth degree. So again, key thing is the polynomial function has positive whole number exponents. So that's something that they could just throw a polynomial or what they were trying to call a polynomial at you and you don't even see the graph. But if you see like a 4/5 power, you're like, oops, I know that's not what I want. Because look, 4/5 is not a whole number. Okay, so it can be like true or false. Is this a polynomial, yes or no? All right, so if it is a polynomial, we're going to be wanting to graph it, talk about it, and so forth. So the first objective is determining the end behavior. And that's what we just ended on. If it's an even degree polynomial, so this is very, very wordy, but the leading term test here says the leading term is typically your highest degree, so it's the degree of the polynomial. If it's even, so remember that's called an even degree polynomial, notice it's doing exactly what we said it was going to do. If it's an even degree, think parabola, okay? So an example of this would be y equals x squared, right? It's just your typical parabola. It's an even degree. It's opening up because our a value is positive, right? That's what that's saying. So the arrows are going up. We don't know what's necessarily happening in the middle because there might be more stuff going on. Here, this is the same thing. It's an even degree polynomial, but our a is less than 0, meaning it's negative. So which way is it opening? Opening down. So an example of this would just be y equals negative x squared. So even though the quadratic, the parabola, guys, isn't the only even degree, it's my reference. You know what I mean? So like if I see a 4th degree or 6th degree, I think, okay, parabola is going in both directions. Now an odd degree, we talked about it, your odd degree ends are going opposite. So the typical cubic is going down and goes up. So that's when your a is positive. So that is y equals x to the third. So these are odd degree polynomials we're talking about here. So y equals x to the third, that's not very, I feel like I got to write darker. But again, that might be to the third, to the 7th, to the 100th and 1st. I don't know. If it's an odd degree, it's going to go that way. And then flip about the x-axis is when you make that a term in front negative. And so this is just similar to y equals negative x cubed. And what's funny is like they're kind of even telling you right here, that weird slashy part in the middle of your graph is not determined by this test. We don't know what's happening in the middle just from the leading term, okay? The leading term is going to tell us which direction it's opening and what direction our ends are going. There's going to be other things to see, and I think 4.3 is where we like do everything in the middle, okay? So with that being said, can we use that information to match each of these 4 polynomials to the correct graph? So I'm going to look for, is my a term or my first term positive or negative? So I know it's either opening up or opening down. And is my degree of the polynomial even or odd? So I know both ends are going in the same direction or they're going opposite directions, okay? So looking at this first, we have 4th, 3rd, 1st. So this is the 4th degree, so it's even. So what are our ends doing? Same direction or opposite directions? They're going up, yeah, they're going same, and then they're going up because it's positive, right? So I'm going to just kind of make a note of that. So we're opening up, and then we're kind of doing that. Again, remember that little squiggle in the middle means I don't really know what's going on. So looking at A, B, C, D, of those 4 graphs, which 2 ends are both going up? D. Perfect. Then I'm going to look at B, little b, on our polynomials. This is 3rd, 2nd, 1st, 0. So this is a 3rd degree polynomial, but notice our a value is negative. So this is technically opening down, and our opposites are this way. The cubic's a little bit harder to remember what down is. You know what I mean? Like, so you just have to think the normal cubic goes from low to high. So when you flip it, it's high to low. So who's matching that? B. This guy, we can have a 1/4 as a coefficient. So I'm stressing these whole numbers, whole numbers, whole numbers. It's whole numbers as the exponent. So a coefficient of 1/4 is fine. That's fine, okay? So we have 5th degree, 1st degree, 0 degree. So this is a 5th degree, but we're opening up because it's a positive A, right? So that means we're going to do our normal kind of like cubic looking guy. So who does he look like? A. And then process of elimination, but let's just make sure it makes sense and they're not trying to trick us. On D, we have 6th, 5th, and 3rd, so it's a 6th degree polynomial, so that means our ends are going the same direction, but we're opening down because we have a negative A value, so that means down. So I know it's weird, but when I've taught it before, I feel like devil horns up or down, so like devil or bull, and then like the odds like me dancing. It's like the disco kind of thing, and that's basically what we're doing. Are there any questions on end behavior? Okay, so we can tell two things, whether it's opening up or down based on the leading coefficient sign, and then we can tell what way our ends are going, both up or opposite directions, based on our degree of the polynomial. So that one is, what answer does that go with? C? Woohoo! Okay. So after we get kind of the end behavior, we want to start seeing what's happening in the middle. And the first thing they have us do is find the zeros. Well, if you remember on the front page, I said the zeros are basically just the x-intercepts. So it's where our function equals 0. It's when y equals 0. So we're going to be factoring, or we're going to be using our calculator one way or the other. So looking at objective 2, it says, if c is a real 0 of a function, then that means when we plug c into our function, our y value is 0. Okay? So that it's technically just, so a 0 is an x-intercept, guys. So this one, they were really nice to us. This is actually a quartic. How do I know it's to the 4th degree? It's because if I multiplied all my x's, it'd be x to the 4th, correct? They were nice. Instead of having it all multiplied out term by term, they've already factored it us factor, so we can easily pull our zeros. Because how do you find the zeros of a function? You make the f of x part 0, and then you set each of you factor or whatever you need to do. So this is just 0 equals 5 times x minus 1 times x minus 1 times x minus 1 times x plus 2. And since they were nice and factored it to us, what do you do after you factor it? You set each of your factors equal to 0. Do we really need to actually write x minus 1 3 times and set it equal to 0? No, we're just going to solve it once and we'll get an x value of 1, right? So we're going to just set x minus 1 equal to 0, x plus 2 equal to 0, and solve. So x is going to be 1 and x is going to be negative 2. So our zeros are just going to be negative, oops, why am I putting negative 1? Sorry, positive 1, negative 2.
What do we do with the 5?
You can set him equal to 0. That's a good question. But can 5 equal 0? Like, is there anything to solve there? No. But I'm glad you pointed that out because it might be a 5x, and you would want to set 5x equal to 0, divide both sides by 5, so x equals 0. So yes, so if that leading term, that number in front has a variable with it, set it equal to 0. But if it's just a number, it can't be 0, and so there's nothing to solve. Okay? So, okay, great. We have these 1s and this number 2, but like, notice that the 1 was there 3 times. That's kind of suspicious. Like, what does it mean that it showed up 3 times? Does it go through the graph 3 times, or what exactly does it mean? That's called the multiplicity. And so the multiplicity is just the exponent of your factor, okay? So guys, what would be another way to write x minus 1 times itself 3 times? To the 3rd power. So it would technically have a multiplicity of 3, all right? How many times did we see x plus 2? Just once, so it has a multiplicity of 1, all right? Why do we care? Because kind of like our even and odd degrees, we know what directions our ends are going. Our even and odd multiplicities let us know whether we're crossing at the 0 or just going down and coming back up, okay? So here, guys, k is the degree of the factor. That's why they're not using n, because you're like, okay, well, we talked about n being the degree. Why are we throwing k's in there now? Because n is the degree of the entire polynomial, k is the degree of the factor. So if you have an odd k, it's of odd multiplicity, okay? So let's draw a picture. So I'm going to just draw my little XY plane, okay? Has anybody taken trig or seen trig before? Have you guys heard of, or a baby version of it, sine, cosine, all that, right? So the sine graph is kind of a good example of crossing. So this is this is the cosine graph. It goes down, comes back up, and then keeps going like that, okay? These here, these zeros, notice we're crossing through them, correct? So they would have odd multiplicity. I can't spell. Multiplicity equals cross through. And they're just saying that over here, but it's a little fancier. So if k is odd, then we're crossing at those zeros.
Doesn't have to cross through twice.
No. Like I could have stopped here and just grabbed. So this is 1 0, that's a second 0, okay? But they both would have an odd multiplicity because we went through at those points. Now if k is even, let's draw this guy. He is just going to come down, touch, and then go back up. So if it's even multiplicity, touch and go back. AKA they call that tangent. Have you guys heard of the term tangent before? It's where you hit at one point, but then you go off. Like, that's why I say you go off on a tangent. You started at a certain point, but then you kind of flew off into a different direction. And that's just the whole idea here. It comes down, it actually touches there. So it's very close to the x-axis, but then it goes off in a different direction. Again, I kind of think of my even and odd graphs, right? A parabola kind of has that touch where it goes down and comes back up. And then the odd, the cubic, you know, it's that snake function where it's just going to be crossing through and it's going to keep going, okay? So why do we care about this? Because when we start talking about zeros and we start graphing them, we're going to know, oh, when we graph it, it's going to go through, or nope, it's going to touch and come back down the direction it came from. So let's look at these bad boys on the back of page 4. Let's talk about the zeros and then let's list their multiplicities, okay? So it says, find the zeros algebraically of f of x equals x cubed minus 2x squared minus 9x plus 18. You're like, how do I even begin to find zeros? Remember, zeros means set it equal to 0 and start solving. This is a 4 term. 4 terms, guys, way back when in the beginning of the semester with me, was the very first thing we ever graphed. It was the factor by grouping, right? It's the middle part of the AC method. So this is going to be 0 equals x to the third minus 2x squared minus 9x plus 18. So we're going to look at these first two terms. What can we pull out of x cubed minus 2x squared? Not just x, but x squared. Yep. So x cubed, take away x squared, leaves us with an x. Negative 2x squared, take away the x squared, leaves us with a negative 2. Is that all right? And then what can we factor out of the back half so that x minus 2 is left?
9.
Not only a 9, but a negative 9. Okay? We can't do the x because the 18 doesn't have the x, right? So negative 9 divided by negative 9 is an x. 18 divided by negative 9 is a minus 2. Woohoo! Remember, celebrate the small things in life. So x minus 2 is going to come out in front, which leaves us with x squared minus 9. That looks fishy. Can we factor x squared minus 9 further?
Yeah.
Yes. Okay. What were we going to say? Do you remember what it factors to? It's called the difference of squares.
X squared and then negative 9.
But like, what we take the square roots of both, right? So what's the
square root of x? It's going to be x.
X, and then what's the square root of 9? 3. So it'll factor to x plus 3, x minus 3. I'm actually not going to factor it that way. Why? Because I don't want you to think everything has to factor. That could be a 5, and we could still solve it when we set it equal to 0 because we'll just do the square root property, which is kind of like one of the ways we can do it. So we're going to just have, actually, I'm going to switch the order I have it. We're going to set each of our two factors equal to 0. solve for x with x minus 2 is just a matter of moving the 2 over, right? So that's just going to be x equals positive 2, right? But over here, when you move the 9 over, you have x squared equals 9. But how do you solve a square? You take the square root, and when you put the square root there, what don't you forget to put in front? Plus or minus, right? So this is x equals plus or minus 3. So guys, over here I'm going to list our zeros. We have 2, 3, and negative 3, and they're all multiplicity of 1, correct? They only showed up, x minus 2 only showed up once. If we were to factor x squared minus 9, we would have had x plus 3, that's where the negative 3 would have came from, or x minus 3, that's where the positive 3, but we only would see them once. So there's our zeros. But like I said, right here, like Corey saw the difference of squares, you could have factored this to x minus 2, x plus 3, x minus 3, and you would have gotten plus or minus 3 that way. But the reason why I wanted to solve it this way is because, guys, even if that's a 5, then you just have plus or minus the square root of 5 as your zeros, okay? Your zeros don't have to be perfect little whole numbers. They can be square roots. All right, that's actually what happens in this next one. So find the zeros algebraically of this one. So how do we find the zeros? That means set this equal to 0 and solve. So this is actually the AC method, but when we go to split up the first term, instead of x squared split into x and x, we're going to have x to the 4 split up as x squared, all right? So just kind of keep that in mind. So our A is 1, our C is negative 33. What are factors of negative 33 that add up to 8? 11 and 3. Because 33 only splits up two ways, 1 and 33, that's not going to get us to 8, and then 3 and 11. What combination gets us to a positive 8? The 11 is positive, the 3 is negative, okay? So I'm going to write this as 0 equals x to the 4th plus 11x squared minus 3x squared minus 33. So notice I kept the first term as the same degree. And this x squared, he split to 2x squareds, right? Like, because if they split to x and x, they're not like terms. And then we're just going to do factor by a grouping from there. What can you take out of the first two terms? X squared. And when you do that, you'll be left with x squared plus 11. Does that look right? Yeah. Okay. What can we take out of the back two terms so it looks like x squared plus 11? Not just 3, but negative 3, because we want the signs to change. All right. Celebrate the small things in life. We have that repeating factor. So 0 equals x squared plus 11 as one factor, and x squared minus 3 as another factor. So we're going to set each of those factors equal to 0 and solve for x. And these are going to be the square root property for both, because we can just move the constant over and take the square root. What happens when we move the 11 over? It's going to be an imaginary number. I'm going to go ahead and do it, but I'll talk to you about why it's not considered a 0. So we'll have x squared equals negative 11, and when we take the square root, we have x is plus or minus root 11i, technically. I know I skipped a space, but I don't have a whole lot of room in there. Do you guys agree that when you take the square root of a negative, the I pops out? And 11 doesn't break down any, so it just stays under the square root. Now on the right-hand side, though, when we move the 3 over, he becomes positive, so that will be our answer. So this will be x squared equals 3. So what's x going to equal, guys? Plus or minus the square root of 3, okay? So why is the I not part of it? Well, if you go back to our very first definition in here, I really stressed the exponents being whole numbers, but I didn't really stress the coefficients, the numbers, have to be real numbers. Well, we're not going to cross on an imaginary axis, okay? So even though this polynomial, oh, I messed it up. This is a polynomial, so that has nothing to do with it. I think it's the zeros. Where were we talking about zeros? Right, okay, so the 0 is an x-intercept of the graph, but in our world, we don't graph imaginary numbers, so that's why we don't worry about them, okay? Sorry, I went the wrong direction. So if you ever get an imaginary number, it's not considered a 0, all right? So what are our two zeros we actually do have? Root 3 and negative root 3, and they both only showed up once, so they're a multiplicity of 1. Is that okay? And we'll get into, like, I know right so far we haven't seen anything with a multiplicity other than 1, But when we get into further sections, you will, so you'll know what it means, okay? So what does that mean? Like, we're not there yet, but if we were to graph this guy, we're crossing at 2, 3, and -3, and we're going through that x-axis. Same thing here, at root 3 and -√3, we're flying through the axis. We're not going to touch and go back where we came from.
On this one,
Yes.
it's just a root 3 and that one's a regular 3.
Because I didn't show my steps, but I'm taking the square root of both sides, and 9 happens to be a perfect square, right? So I missed this step because I ran out of room. What's the square root of 9? 3, because 9's a perfect square. But, and then here, when I took the square root, he wasn't a perfect square. So it's just the difference of what we were taking the square root of, right? And so that will happen though, Corey. I'm glad you pointed out, because sometimes you'll get perfect squares like 16, 25. So those beautiful numbers will pop out. But a lot of times you won't. So a lot of times you'll have root 5 or root 4 or something like that. Or root 4 doesn't make sense. That's a 2.
So
But
you can't use like a radical?
no, you can. We used him. We can't use I, the imaginary numbers, okay? Because a radical, we're really judgy. We're like, ew, you're ugly. But he's a number. If you put the square root of 3 in your calculator, it's 1 point blah, blah, blah. So he's going to cross the graph at 1 point blah, blah, blah. Let's see what square root of 3 is.
He's not too bad.
Let's clear that. Square root of 3. So he's approximately 1.7. So radicals are okay. It's just this one had an I as an imaginary number, and you guys, unless you're going to be math majors, do not need to know about graphing in the imaginary number system. Does that make sense?
Yeah.
So the radical's okay. That's why I listed him over here. Okay? All right, so the last one, guys, is sometimes you're going to get ones that just are not factorable. So you are going to have to use your graphing calculator to find those zeros. So you guys, let's write notes here so we have notes to refer to, and then we'll get our calculator and do it, okay? So in our y1, guess what we're graphing? X to the third minus 1.2x plus 2, okay? So I'm just kind of writing it like how you would type it in, right? X caret 3 minus 1.2x plus 2. And then we're going to hit graph. And if it's not good, hit zoom and then 6, which is standard. And it should get you to your normal viewing window. And I'm 99% sure in this section, most of them will be in that normal viewing window. If not, you can play around with the window. All right. So once we get there, guys, we have to use our calc feature, which is second trace. So we're going to use second trace, which is our calculate feature. And we're going to use number 2, our 0 feature, okay? And that's all the more I'm going to really write because depending on what your graph is, it's going to depend on where we do. So your 0 feature, the key thing with your 0 feature is you have to do 3 things. You have to have your cursor at the left of the 0 and of the right of the 0 and then hit enter, okay? So you're going to have a left bound, right bound, and then hit enter, all right? We'll make a note of that. Left bound, right bound, and then you're going to hit enter one more time, okay? And why I'm stressing that is because depending on whether your graph's opening up or down, your left bound might be above or below the x-intercept, and then you cross over, and that's where your right bound. So I don't know, are we going to be doing this or this? It depends on our graph, okay? So these should be enough notes for you to kind of refer to when you go to do your homework and your worksheet. But let's actually do it and make sure it makes sense. So make sure our notes are good enough. We're going to go to our y equals feature right here, and we're going to type in our function. So I'm going to clear this out, and I'm going to do x to the third minus 1.2x plus 2. I'm going to hit graph. Okay, so notice my graph, it's kind of small. So I'm going to hit zoom standard, which is 6, just to make sure it's the standard graph, and it might not have changed anything. It zoomed it in a little bit for me, okay? So guys, what is a 0? A 0 is an x-intercept. So how many zeros do we have in this graph? 1, okay? So that's something to kind of keep in mind too, that it's not always the degree of the polynomial. Like we had a 3rd degree polynomial. We're only crossing once, all right? So we want to know where he's crossing. He's crossing somewhere between -1, -2, but we're going to be able to figure out the exact number. So how you do this is when you, yes?
You got like 27.
Oh gosh, okay. How you do this is we're going to hit second trace and we're going to use the 0 feature 2. The left bound will be down here. We're going to hit enter, cross over. The right bound will be here.